Boker Tov, good morning. Okay, ביקשו ממני להשתמש באנגלית, so we'll do this in English. Hi everyone, my name is Hagai Lupesco. I'm an engineering manager at Facebook AI, working at Personalization. I'm based in Menlo Park in sunny California. And today I'm going to talk to you about personalization or AI-powered personalization at Facebook scale. So what will we cover? We'll take a good look into what personalization actually means, how it's engineered, what are the challenges of building and shipping effective personalization models at scale. If you'll stay tuned throughout the talk, and I know you're probably hungry because we're before lunchtime, but if you will learn practical techniques you can apply in your projects to make your machine learning workflows and models more efficient and effective, and how to overcome challenges that will probably come up. I hope you'll enjoy the talk and learn new stuff. I'll be here after the talk if you want to say hi or just ask questions or connect. All right, so let's get started. Actually, I want to start with Facebook's mission. And Facebook's mission is bringing the world closer together. We do this through our platform of applications and services that are connecting more than 2 billion people across the globe today. So that's truly an immense scale, and we'll dive into a bit more of what this scale means in a couple of minutes. So one of the key ways we're bringing the world closer together is by connecting people to content and communities they care about or that can have positive impact on their lives. And AI-powered personalization is key in doing that effectively at the scale that Facebook operates in. So, you're probably familiar with Facebook's, one at least of Facebook's apps or services. And just to showcase how personalization is used in these apps, I'll just give a few examples. So if you look at the Facebook feed or Instagram's Explore experience, when you enter the app, you actually see a list of posts or items that are tailored to what we believe is your interest areas and things you're likely to engage with or find interesting. If you look at Facebook groups, we are actually recommending groups to you that might be useful and have a positive impact on your lives. If you look at Facebook Marketplace, we're surfacing items we think you may be interested in purchasing. Now, when you look at the scale of all of this, it's truly immense. I think there's probably only a handful of companies across the globe that are actually operating in this scale. We're talking about more than 1.5 billion daily active users across the platform. And if you look at monthly active users, it's somewhere around 2.7 billion. We're talking about billions of posts shared per day on the platform and hundreds of billions of posts being impressed or engaged with every day. And this all translates to trillions of ranking calls just for posts recommendations on our platform every day. So that's a pretty immense scale, and it also brings a lot of engineering challenges with it, and we'll dive into them shortly. So in this talk, obviously, we're limited in time. We won't cover everything about personalization, but I chose a few topics I think are interesting and also common across different companies that are trying to address similar challenges. We'll start with system design, how are recommendation systems at this scale typically engineered. We'll talk about candidate generation, which is one of the first stages in a recommender system at scale. We'll talk about how you learn from sparse data and combine it with dense data for your heavy machine learning ranking model. And lastly, we'll briefly talk about practical techniques to keep your models fresh. Okay, let's start with system design. So personalization use cases are delivered via a system that is typically referred to as a recommender system. And we start with the basic definition. So given a query input, which may include attributes like user ID, time of day, different device attributes, location, etc., they flow through the recommender system, and the recommender system returns a list of items that are ranked, so they're sorted. And those items are items the system, the recommender system, thinks are tailored to the query and the user from which the query came from. There are two other subsystems that are worth mentioning. One is the feature store that is used by the recommender system. It contains a set of features for the query and the items, and an item store, which is a repository of the items. Now, if we zoom in into the system, it's obviously a bit more complicated internally. Now, every different application or service in Facebook that is doing recommendation or personalization is has its own unique characteristics. In this slide, I'm actually not looking into one specific system, but rather kind of taking the general approach that is used across most of these systems. So let's start in the first step. So a query comes in from the end device, like a mobile device or a browser or another service. And then it's handled by the first stage, which is called Retrieval, or sometimes also referred to as candidate generator. So the candidate generator goal is to go over the set of millions or tens of millions or sometimes even more items and extract a much smaller set, usually in the order of thousands of items that the system thinks are probably a good fit for this specific query and this specific user. The focus is not on accuracy or on ranking accuracy, it's more on recall and also on low latency, because taking items in the millions or tens of millions or more and condensing them into a couple of thousands is in a short amount of time is pretty difficult, and we'll dive into a technique on how this can be done. Then the smaller set of features goes into the ranking model, which is a heavier machine learning model that focuses actually on precision and on ranking accuracy. That's usually a heavy model. Usually it's also based on deep learning, and we look into some potential architecture for such a model. But this model is able to take these thousands of items and return around 20, 30, 40, 50, something in that order that are ranked in high precision. Lastly, the last but not least, there is a layer of, usually you have a layer of custom business logic. So, traditional human programmed rules to filter things further and apply things like, maybe user specifically disliked a certain type of items or a certain type of, source of the items, etc. So there is a layer of filtering. And then it all flows back to the end device where it's presented to the user. Now, one very important step is that the actual interaction of the user, both the impressions and conversion events, have to be logged back into our impression logging system, because it's going to be used later for training the model. So small step, but super important, because our models are only as good as the data they're trained on. Now, all of this has to complete in typically under 1 second, sometimes even under 500 milliseconds, because the user experience on the end device is critical. All right, let's zoom into candidate generation. That's the first phase. So just to clarify the challenge, identifying hundreds of items out of millions of items and do it extremely fast. The practical approach, as we've shown, is multi-stage ranking with a candidate generator on the first stage. The technical requirements from the candidate generator is optimizing for a recall, right? So coverage for the top items. Do not optimize for accurate ranking, but rather optimize for latency, because usually that stage is latency bound. So I'll briefly talk about, there are different, like any interesting problem, there are different techniques that this problem can be addressed or solved. I'm going to look into one that I think is pretty interesting, is useful, and we're definitely using it. It's using embeddings. So how many of you here are familiar with the concept of embeddings? All right, great. So most of you are. I'll briefly go through that. So basically mapping high dimensionality feature space into low dimensionality vector. And everyone knows the usage of embedding in NLP, things like word to vec, and ability to map a word into a dense vector, a low dimensionality vector. And when you think about features of the type we use in recommender systems, these features may be, a post ID that the user has engaged with, or a video ID that the user has watched. Now, actually, nothing prevents us from mapping embedding from a video ID into a set of dense vector that preserves the latent structure of that video. So that vector actually is a dense representation of the content in the video. So when you present video IDs this way, two videos who are similar in their content will actually be close in their distance. Similarly, we can also use that on post IDs, and there are other ID-based features that can be represented this way with the dense vectors. And we'll talk more about this technique and how it's used. Okay, let's skip the king minus man example because everyone's familiar with that. But how can we use that for retrieval? So using embedding. So one approach is to use what's called a two-tower neural net. So a two-tower neural net is a neural network that is comprised of two sub-neural nets, the two towers. One tower is the query tower that takes in the query features, maps them into an embedding. And then the other tower is a tower that takes item features and maps it into an embedding. Now the tower itself is a neural network. We won't dive into how this is implemented, but it outputs a dense vector. And then we connect these two with some sort of similarity function, some kind of vector interaction that then outputs a scalar for us. And when we actually take this neural net, we train it of the task, for example, of engagement. So user, engaging, for example, with the post, or if it's a video, user watching the video. We actually take our data and we train our neural network. And at the end of the day, we have a trained neural network with two sub-neural networks that we can use separately to produce embeddings. Okay? And let's see how this is used in practice. So the first stage is offline. Basically, an offline processing, we go through our item store. We use our item tower from the big neural network we trained earlier to produce an embedding for each item, and we store it in a KNN service. Now, KNN is K nearest neighbors indexing service. It can be a talk by itself to talk about efficient implementations of KNN, but there's a lot of literature about that. There's libraries, even Facebook also open sourced a library called Facebook AI Similarity Search that has approximate K nearest neighbor search that is very efficient. So the idea is to use such a service, KNN, to index all of the embeddings for your items, and that's all done in offline. Now online, when a query actually comes into the system for retrieval, we take the query features, we pass them through the other sub-neural network, our query tower, we get an embedding, and then we go to our KNN service to do a fast lookup of a set of K nearest neighbors in our KNN service index. And that gives us the set of embeddings that represents items that we're going to return back for the candidate generation phase. So that's one technique. It can be very efficient, low latency, that is used effectively in such systems to address the first stage, which is the candidate generation. Okay? All right, let's talk about learning from sparse data. I think we spoke earlier about the importance of data in our machine learning model, and the quality of our model is really bounded by the quality of the data the model is trained on. But there is something unique about machine learning personalization models, and that's the fact that their training data is a combination of dense features and sparse features, and I'll explain a bit more what this means. But so when we talk about dense features, we talk about continuous numerical features. For example, a user age is a continuous feature. The other set of features is categorical features. We spoke earlier about post ID or video ID or language ID or device ID. These are all categorical features. They're not continuous. They're ID based, sometimes count based. And learning from them in a neural network is actually a bit different than how we learn from dense features. So again, examples for dense features are, user-reported age, time of day, number of posts the user liked in the last 30 days, or the number of videos the user watched in the last week. Usually, numerical proximity in these features also means semantics proximity. Categorical features are very different. Again, they're ID-based. two posts with very close ID in the numerical sense are not necessarily very close in the semantics of these posts or of these videos. That's why we need to learn these features in a different way. Okay, so let's think about how we can learn from both. We'll start with dense features. That's actually pretty trivial. That's what we're used to doing. And in this example, we have a set of dense features like, again, age, time of day, 30-day post clicks. We'll usually have a normalization layer that would condense these numbers into, normalize them into a certain range, usually -1 to 1. Then we'll concatenate the normalized values into a vector, and we call this vector a dense vector because usually, it will have very few zeros, if any. And then we'll take this vector and we'll feed it into our neural network. So that's so far so good, nothing new. With categorical features, we're handling them a bit differently. So we'll have as an example here, the language ID. We have the set of post IDs the user liked in the last month, and video IDs the user watched. So how do we handle these? So one way to do it is to use embeddings. So we spoke about embeddings earlier, and we're reusing that concept here. But we can actually have an embedding, just like we have embedding for learning natural language processing related tasks. We use embedding tables that allow us to do a lookup from the specific item ID into a dense vector. Then that dense vector will want to find the ways to produce a meaningful dense vector that combines everything. Now, there are different ways to do it. One way is to just concatenate all the dense vectors coming out of the embedding table. That will usually produce a really huge vector. Other ways are to do Pairwise Dot Product, where you do vector interaction across the different embeddings. And simple way to do it is just to do dot product across pairs of these vectors and then get a set of scalars. Notice that when we talk about a set of IDs, for example, one feature for a recommendation system may be the items the user engaged with in the last 30 days. Like the videos the user watched in the last 30 days, you actually have a set of embeddings. You want to do something like pooling, for example, max pooling or average pooling or the other types of pooling, which will allow you to get eventually just one dense vector that is representing that feature. And then again, you'll feed it into that layer where you do pairwise interaction. You take the output from all of these pairwise interaction, which are scalars, and you combine them into just one dense vector, which then is a dense vector, and we're able to feed it into the neural network. So that's one way we can learn categorical features and later combine them into the big picture to be trained with the dense features. So how does this all work together? You can see here an example reference architecture for a recommendation system that is learning on both dense features and sparse features. This architecture has actually been open sourced by Facebook. Facebook internally uses variations of this specific architecture very successfully. Again, it was open source. You can look it up. There's a PyTorch implementation. It was trained and tested on a Kaggle dataset competition, and it beat the best result in that competition by far, and without doing any optimization. And I guarantee that if you play around with the model, fine-tune the hyperparameters, tweak it a little bit, you'll get much better results. Let's take a look at this architecture. So we have two inputs into the net. One is the set of dense features, one is the set of sparse features. The dense features go through a bottom MLP, so multi-layer perceptron, a few layers of dense layers, and then it outputs vector. The sparse features go through the embedding tables through the layer I've shown earlier to get another dense vector. Then we are interacting these two vectors through feature interaction. That's kind of the secret sauce that is application specific. How do you actually implement that interaction? A very simple way to do it would be concatenation, but you can do a bit more complicated stuff that I won't go into here. At the end of the day, you get another vector out of that layer. You feed that into what we call the top MLP, the top multi-layer perceptron, to learn additional interactions. And then we take it into the actual prediction, which depends on the task at hand, but it can be, for example, likes of the post or watches of the video. And this is the network we train to be used later in that second stage of the multi-stage ranking. So you can check it out, open source with the PyTorch implementation. It's called DLRM, Deep Learning Recommendation Model. Now, a few interesting observations about this architecture. It's actually pretty unique, and it's pretty different than the usual suspects of vision models or NLP models that everyone's talking about. First of all, the computationally intensive parts of this network are just the MLPs. MLPs have usually a lot of parameters. Computationally, they're not as extensive as convolution. But then the embedding tables are actually the interesting part of these models. They're usually memory bound. There's hardly any computation involved in an embedding table. It's basically just a lookup table. It can be implemented with just a simple hash table. But because production grade models for personalization have really a lot of sparse features, and in Facebook's case, it's hundreds or thousands of sparse features, these embedding tables are huge. And in size, they can be in the area of tens of gigabytes, hundreds of gigabytes, or even terabytes. So that's the majority of the parameters of such a network is actually in the embedding tables. And that's also creates a lot of challenges in how you actually train this model. Because if you try to train a model that is hundreds of gigabytes in size, you actually can't do it on most GPUs because you don't have enough memory. So usually you're confined to training on a CPU, and you actually usually need to implement what's called model parallelism. So again, if you think about most, for example, production grade vision models, usually to train them you use data parallelism. So you have a lot of data, the model can fit in just a single GPU, so you split up the data and you do distributed training. In these models, this will not work because this model cannot fit on just one node. So you actually have to split your model into multiple hosts and train it. And it creates a lot of complexity. And that's one of the actually difficult parts in how you train these kinds of models. The good thing is that it actually works pretty well. Okay, so lastly, we'll talk about how to keep our models fresh. So keeping models fresh and up to date is a challenge because in most applications, nothing is stationary, right? Items are added, removed, updated every minute. Your users are onboarding and changing. They change in their preferences. They change in what they're interested in pretty often. So our data distributions are constantly changing, and it's important that the models are updated accordingly. So how can we keep up with our models? How can we do that while staying efficient in our compute? There are two ways I want to illustrate that are effective ways to do it. One way, which is actually not as common, but it's important for really critical, business critical models, are what we call online training. We actually train the model as user interaction data is captured. Not with every interaction, but we batch them, aggregate them, and it can be that the model is retrained every couple of hours, sometimes even less. So in online training, you actually deploy an updated model every few hours or less. Usually it's implemented by fine-tuning the last baseline rather than training from scratch, because usually you don't have enough time, you don't have enough data, and also you want to be efficient with your compute. And that's really something you want to do only for models that either your data distribution change very rapidly, or your model is business critical, like it's responsible for a lot of your revenue. Then you want to actually make sure this model is always up to date and very sharp. The other method is recurring training, and you can, by the way, implement both I would actually recommend implementing recurrent training for any model you have in production, and I'll explain why in a minute. But this is basically training on offline data in repeat. How often? It really depends on your business use case. It can be every day, it can be every week or every couple of weeks. But you want to make it the default practice for your models, because otherwise you're really risking to have models in production that you're not actually able to retrain and update when you need to and when it's critical. Because the reality of the work we do is that a lot of things are changing and moving. Your software infrastructure is changing, your features are changing, being updated, removed, added. And if you don't make sure your models are always up to date, just like your software, by the way, you want to also make sure you're able to rebuild your software and you want to deploy often, exactly the same with your models. So usually recurring training is implemented with some kind of recurring job. Usually you're training from scratch, or you fine-tune a baseline, but usually you want to train from scratch because you have enough data, you have enough time. But that's a cost-benefit decision you can make. So these are the two practices for keeping your models fresh that I highly recommend you follow. Okay, so our time is almost up. Let's recap what we went through. So we reviewed the typical system architecture for a large-scale recommendation system. We looked into the requirements of a candidate generator and how it can be implemented using embedding-based KNN system. Then we learned the challenge of learning from sparse data and combining it with dense data, and how we can architect a network that is able to combine both and learn an effective recommendation task. And finally, we understood the challenges of keeping models fresh and up to date and how we can do it. These are all important key aspects of designing production-grade and at-scale recommender systems. Okay, I hope you learned new and useful stuff and that you also enjoyed. If you have any questions, you want to say hi, I'll be here now and later today. Feel free to drop by and say hi. And lastly, I just want to say AI is a super important aspect that we're working on at Facebook, and we're also hiring a lot for AI-based positions in Menlo Park, in New York, and also here in Israel. If you're interested in learning more, come drop by, say hi, or find me on LinkedIn. I'll be happy to help with that. All right, thank you.